This is a video presentation about heat exchangers, and I'm going to explain you how the different formulas are derived related to heat exchanger analysis. This information will be really useful when you do a model of a system that includes a heat exchanger. So, mathematical modeling of heat exchangers, what you need to know with mathematical modeling minds. This is the outline of this video. What is a heat exchanger? Types of heat exchangers, total thermal resistance, log mean temperature difference, and NTU method. What is actually a heat exchanger? A heat exchanger is a device that helps the heat to be exchanged between two fluids at different temperatures, and the fluids are separated by a wall. There are different types of heat exchangers. They can be classified according to the flow arrangement and method of construction. Concentric tube heat exchangers are the simplest of all heat exchangers. They can be either parallel flow type or counterflow type. In parallel flow heat exchangers, the two fluids flows in the same direction, and in the counterflow type, they have opposite directions. The first figure shows parallel and counterflow heat exchangers, and by looking at the arrows, you can see how the flow is arranged in each heat exchanger. In cross-flow heat exchangers, both finned and unfinned designs can be found. In finned type, both fluids are unmixed, and unfinned type, tube flow is unmixed while the other fluid is mixed. This is shown in the second figure. In shell and tube heat exchangers, different configurations are available according to the number of shell and tube passes. Usually in these heat exchangers, baffles are installed to increase the convection coefficient of the shell side fluid by inducing turbulence. Also, baffles physically support the tubes. Compact heat exchangers are used to achieve very large heat transfer surface area per unit volume. These heat exchangers have at least one of the fluids as gas. Next, we look at the total thermal resistance R. The overall heat transfer coefficient U represents the total thermal resistance to heat transfer between two fluids. Thermal resistance is given by 1 divided by UA, where A is the surface area of the heat transferring surface. And what is fouling? Fouling is a film or scale on the surface due to fluid impurities or rust formation between wall material and fluid. Fouling factor RF is a thermal resistance term used to address these phenomena. The resistance to heat transfer can be reduced by introducing extended surfaces, which are called fins. Now let's see how the formulas are developed for calculating the total thermal resistance. Here is the temperature profile of a heat exchanger. I'm going to develop a formula for the resistance to heat transfer. And here we assume that hot side and cold side surfaces are equal in area. The heat flow at the hot side is equal to QH, which is equal to HH times A times TH minus THS. HH is the heat transfer coefficient at the hot side, and A is the heat transfer area at the hot side. TH minus THS is the temperature difference between hot side and the hot side temperature. And this is a convection mode of heat transfer. The heat flow along the wall is equal to QW, and it is given by KW times A divided by LW times THS minus TCS. Here, KW is the thermal conductivity of the material, and A is the surface area, and LW is the thickness of the wall material. THS and TCS represents the surface temperatures of hot and cold sites. And this is a conduction mode of heat transfer. The heat flow at cold side is equal to Qc, which is equal to Hc times Ac times Tcs minus Tc, where Hc is the heat transfer coefficient at the cold side and Ac is the surface area at the cold side. Tcs minus Tc is the temperature difference between the surface temperature of cold side and the cold side temperature. And the heat flows QH, QW and QC are equal. So we can add these three terms to get the formula for total thermal resistance. As we discussed earlier, extended surfaces are used to reduce the resistance to heat transfer. The figure shows a wall of a heat exchanger where extended surfaces are used. The red color shows the fouling. And we use the highlighted formula for calculating the thermal resistance in such heat exchangers. An efficiency eta naught is introduced, which is the overall surface efficiency. And Rf double dash is the fouling factor and Rw is the resistance due to wall material. Log mean temperature difference. What is the log mean temperature difference and why we need it? LMTD is a method used to analyze the heat exchangers. For example, it can give an idea how good a heat exchanger is performing. Higher the LMTD, good chance for effective heat transfer. In order to apply this method, it is important that we know the inlet and outlet temperature of both fluids. If only inlet temperatures are known, applying this method involves a lot of iterations and hence not effective. There are two main relations that represents the heat flow rate of a heat exchanger for analysis or modeling. They are mCp delta T and UA delta T. In order to find the mean temperature difference delta T, we use LMTD method. Next, we can see how the equation for LMTD is derived. Now we are going to derive the formula for LMTD in a parallel flow heat exchanger. We first apply the energy balance for the hot fluid to a selected control volume of dx length. Before applying the energy balance, we have to make some assumptions. The heat exchanger is insulated from surroundings and the heat exchange is only between the two fluids. The potential and kinetic energy changes are negligible. Specific heats of the fluids are constant, even the temperatures are subjected to continuous changes. Internal energy of the fluids are constant. The axial conduction through the heat exchange tubes are negligible. So these are the assumptions we used in this modeling. Tq is the heat transferred from hot fluid to cold fluid within the selected section. And we assume the temperature of hot fluid is changed by dTh amount when leaving the selected control volume. Tref is a reference temperature used to measure the enthalpy. We apply the energy balance for the hot fluid for the selected control volume. The energy flowing in is equal to m dot h Cph times Th minus T reference. And this incoming energy is equal to the energy losses, assuming steady state conditions. So energy losses are dq plus m dot h Cph times Th plus dTh minus Tref. By integrating this formula, we come up with this final form as Q equal to m dot h Cph times Th in minus Th out. Next, we apply the same procedure for the cold fluid. So we can get the equation that Q is equal to m dot C times Cpc into Tc out minus Tc in. So heat transfer across the surface area dA can be written as U delta T times dA. Here delta T is the mean temperature difference between hot and cold fluids, and delta T is equal to Th minus Tc. We take the differential form of delta T equals Th minus Tc as d delta T equals dTh minus dTc, and we can use dTh and dTc from the equations we developed in the previous slide. Then solve this equation for d delta T and then integrate it from delta T1 to delta T2, the left hand side, and 0 to A, the right hand side. After integration, you get a formula for the Q, where Q is equal to UA times delta T2 minus delta T1 divided by ln delta T2 divided by delta T1. This equation is analogous to Q equals UA delta T. So we can use the delta T as delta T2 minus delta T1 divided by ln delta T2 divided by delta T1. And this is called log mean temperature difference. So now we have developed a formula for log mean temperature difference of a parallel flow heat exchanger, and we can use the same procedure for the determination of the log mean temperature difference of a counter flow heat exchanger. But here delta T2 is equal to Th out minus Tc in, and delta T1 is equal to Th in minus Tc out. Effectiveness of a heat exchanger, the NTU method. So, if we know both inlet and outlet temperatures of two fluids, we can use log mean temperature difference method for analyzing the heat exchangers. But when we know only the inlet temperatures, NTU method is used for analysis. Define the effectiveness of the heat exchanger as Q over Q max. Q max can be achieved in counterflow heat exchanger having an infinite length. What is the maximum possible temperature difference in a heat exchanger? It is Th in minus Tc in. In this infinitely long heat exchanger, one of the fluids will experience this maximum temperature difference. The fluid which has the low heat capacity will experience the large temperature change. If it is the cold fluid, it will be heated to the inlet temperature of hot fluid. If the heat capacity of hot fluid is less than the heat capacity of the cold fluid, then hot fluid will be cooled to the inlet temperature of cold fluid. So we can define the Q max as C min times Th in minus Tc in. So the efficiency is defined as Q divided by Q max. Q max is always defined using C min, and we can represent the Q as efficiency times C min into Th in minus Tc in. The effectiveness of a heat exchanger can be written as a function of NTU and C min over C max. NTU is the number of transfer units, and C min over C max could be either Cc divided by Ch or Ch over Cc. NTU is defined as UA divided by C min. In order to determine the effectiveness of the heat exchanger, we need to derive the formula using NTU and C min over C max. Remember I told you that this method can be used to analyze the heat exchangers that we don't know the output temperature of each fluid. Now we are heading towards the building of NTU relations. Consider a parallel flow heat exchanger where C min is equal to C hot. Then we can write the efficiency in terms of inlet and outlet temperatures. We know the relations for total heat transferred from hot and cold fluids. Use these formulas to derive the relation for C min over C max. From log mean temperature difference derivation, we have this formula and we can substitute the relevant temperatures for delta T1 and delta T2. Also use C min and C max instead of C hot and C cold. Now we are able to make the NTU term. Let's take the left hand side of this equation and rearrange it so that we can use the equation 3. We substitute for Tc out and then again take the right hand side of the equation 4 into consideration. Solve the equation for efficiency and here you have the effectiveness formula for parallel flow heat exchangers. Likewise, we can derive the effectiveness formulas for other types of heat exchangers as a relation of NTU, C min and C max. And I'm not going to explain them here in this video. So here is the end of this video presentation, and I hope you understood this session about heat exchanger analysis that are important in mathematical modeling as well. If you have any questions or concerns of the content of this video, please leave a comment. If you really like the video, give thumbs up and subscribe for the channel and press the bell icon for new video notifications. Thank you.